So this should be well within the time, and it's somewhat technical, but I sort of have the secret hope that people will interrupt me if they stop understanding, especially if they want to keep understanding. So please don't hesitate to interrupt me at any point, and it's okay if we don't go into all the details. This is sort of trying to introduce some of the concepts here because I think they're interesting. And I think they're relevant to Haskell, but it's not a talk about Haskell. So it's a little weird to advertise this in my first slide. It is a talk about Haskell-ish things. And in particular, when you say a talk is not about Haskell, it's natural to sort of try and go the high school student writing report route, which is, what is Haskell? The Oxford Dictionary says Haskell 98 is something that I can sort of pretend to understand. It's got a nice definition. It's got features that are, I'd say, modern still, but somewhat integrated. But it turns out when people say Haskell, they don't really mean Haskell 98. They mean whatever is compiled by GHC, which of course, people say, oh, C doesn't really have a semantics, or Python doesn't have a semantics. It's just whatever the compiler accepts. But that's kind of what Haskell is like too, right? It's whatever GHC tells you, after it keeps telling you, oh, add this flag. Okay, I add this flag. And when it stops telling you that, if it compiles, then that's Haskell. In particular, there's a bunch of really scary-looking extensions. Existential quantification, type families, rank n types. We're programmers, but it's kind of scary to see a variable name in a compiler flag. Data kinds, polykinds. Polykinds is still a scary one, though I'm sure you have it sort of by default. Constraint kinds that you actually talked about last month, and something super crazy, and predicative types. People, what?
It doesn't even work. Yeah, it doesn't even work.
So it doesn't even work. I mean, you have flags that tell the compiler do something, and it doesn't even know. It's like I don't know how to compile this. So this is kind of intimidating. It's long syllables, and I didn't even count them, but there must be like 7 or 8 there. And it feels like, okay, no one will ever understand what all these features do. And now you have them all together, so it's crazy. Now Ed is sort of nodding his head. Yes, you will maybe someday understand them, but it feels like a human being with a finite amount of time and energy might be discouraged. So in a way, my talk is an advertisement for a framework called Pure Type Systems, which is a way to understand all these crazy X foobar in a single framework. Okay, so instead of understanding 8 crazy things, you only have to understand 1 crazy thing, which is an improvement. Yes.
8 times larger than?
It's actually quite small. This is something that's really distinctive about Pure Type Systems. It's almost deceptively simple. Now, don't hold that against me when I explain what they are, but it is a very concise way of expressing a very large amount of things, which is really one of the points I wanted to make. All right, so yeah, now's the real introduction. What do programmers do? One thing a good programmer should be able to do is recognize patterns and sort of abstract on them. So this notion of abstraction is really important, and it's more than just programming. It's sort of what we do as intelligent creatures in general. So we recognize when things look the same, and we sort of take that same thing and conceptually make it one thing. In this case, We're going to take these two occurrences of 2, and conceptually we're going to make it a variable, x, and in this case, the value of x is 2, which seems like we've gained nothing except move the definition of this a little bit to the right. But conceptually, this is a really powerful idea. And it's sort of the basic idea behind lambda abstraction. Okay, now, I'm sorry. Maybe I should have used Haskell notation. This is sort of / x arrow x plus x, just in case you're more familiar with Haskell than you are with these funny Greek letters. In fact, the / is, of course, supposed to look like this lambda, and Ed is giving out stickers with lambdas on them. So I'm going to assume you can mentally at least replace lambda and dot by / and arrow. And this idea of, well, here's an object that represents, this thing replaced at every point where I see x is a surprisingly important idea. It seems completely trivial to a programmer, but it's really a nice idea. Yes?
I'd just like to mention that I can verify that this is actually incredibly difficult to teach.
Yes. I mean, the idea of replacing a letter by a number is difficult to teach, but we learn it relatively early, in the sense high school. But this idea of having this abstraction as an object in itself is also hard to teach even beyond high school. And it's so powerful, in fact, that basically this was sort of one of the fundamental ideas behind the models of computation, but that's a talk for another day. Long story short, you can actually make a reasonable-looking programming language with just this construct, this lambda. One sort of variety of this is called the simply typed lambda calculus. And it always amuses me that people often write out lambda in full letters because they're so used to writing emails. So I see in blog posts where you can actually use LaTeX, you see them write lambda. So lambda, the actual letter, calculus. And the simply typed lambda calculus has this feature where every variable is sort of associated to a kind of thing, which is called its type. And yes, it does not talk about Haskell, but I'm going to talk about types. And basically, a lambda is going to appear in the type as an arrow. And I'm explaining things that you already know, but bear with me. And for example, in the simply typed lambda calculus, you can write this lambda x, lambda f of x. Typically, you'd only write one lambda, so it's xf, f applied to x, and this would have some type, which is whatever the type of x is. F takes an x and returns a b, and what you get at the output is a b. And that's all you have in the simply typed lambda calculus. This ability to take these base types and perform these abstractions and these applications, and maybe apply terms to things, and you have a little programming language. What's crazy, and is really actually quite hard to mathematically prove, is that if you do this, you only have terminating functions. Okay? So you're not Turing complete in the sense that you don't have the expressiveness of a real language. And in fact, yeah, you can sort of pre-process all your terms just by doing the reductions, the beta reductions. I'm sorry, I realized I had a nice slide explaining what a beta reduction is. I think I'll write it on this board. Just a beta reduction is the only computation rule we have. Did I move forward? Yes, I did. Which is, if I have lambda x and then some program p, and if I apply that to some argument v, then this computes to, and sort of in the formal world we'll just say it's equal beta to p where x is replaced by b. All right? So this is the only computation rule. And basically it does what you would expect it to do, which is when you apply a program to a value, it just evaluates the variable for that value. And if you do that for a simply typed term, as much as you can, eventually you'll stop. You'll hit sort of the bottom value. And this is really nice. And it's a nice feature. For example, in Haskell, you would say, well, all these lambdas, I'm going to just keep reducing them and sort of as a pre-processing step. And I don't need to worry about whether or not it's going to terminate. Okay, it's like partial evaluation. Okay, so it's nice, but it is a little bit limited. And in particular, it seems kind of silly that in simply typed lambda calculus, you can take this function, lambda xx, and it just has one type. It has, type int arrow int, or, bool arrow bool, and you can't really do these two things, which is apply it to 3 at one point, and then somewhere else in your program apply it to true. This should have a capital T, I guess, but again, yeah, question?
I was just going to mention that when you say use it somewhere else in your program, it's kind of ambiguous, and I mean, you could use it somewhere else in your program as long as you're not like binding it to a name and then using that name.
Yeah, I mean, morally, I'm talking about this as the same creature, right? I'm saying let id equals this, and it has some type, which is going to be a or a for some a. And if I use that creature at two different spots, it has to be applied to something of the same type.
That's the distinction I was trying to point out.
Yeah. And this is, sort of a good thing about your type system, right? Is that you can only use it in coherent manners. But it's also a bad thing because, well, these two uses seem reasonable, and yet they're forbidden in simply typed lambda calculus. So we want to add the feature where somehow, this is polymorphic. You see where I'm going with this. The idea is to add variables at the type level, and then add some kind of quantification where we can say, well, the identity is x arrow x, but for any type x. All right, so far so good. Haskell has this feature. Haskell 98 has this feature. But one thing that's a little bit subtle, and that I don't think we think about that much originally, is that when you have this type for all x, x arrow x, this sort of quantifies over something. It refers to, all possible types. But what is that all possible types? What is the universe of types? If it's only the simple types, which we saw here, right? This is a simple type. Well, that's great. But you could also say, well, why am I not allowed to instantiate this with, for all x, x arrow x? Okay, possibly this x you instantiate it with also contains universal quantification, right? So why not allow that? It's kind of weird though because you have this circularity here where you can replace an x by something that's possibly itself. So you actually get two completely different things. In the first case, you have what's called a conservative extension, which means your typing is more flexible, but in some sense, you don't have any programs that you couldn't somehow write in your old language. Okay, you have the simply typed lambda calculus ++, where you have more flexibility, but not more expression power. Okay, and in the second case, you get something completely different, and this is quite bizarre. You get something called System F, which I'm going to talk about later, and System F is just astronomically more expressive. You get something really different from this simple type system I described earlier. So this is kind of an interesting phenomenon.
Just a quick question.
Yeah.
The simple types are basically just the types of the simple types minus the lambda calculus. So just
Yes. Yes. So the question was, are the simple types I'm referring to here the types of the simply typed lambda calculus? And the answer is yes, absolutely. There are types that look like this. They're base types and arrows. Okay, possibly nested. Yes?
So in other words, a variable that's quantified over in the first option could not have a type that contains a for all, right?
So what does it mean for a variable that contains a for all?
As in, like, if I have lambda x...
well, you can instantiate it.
Sorry,
take it for all.
Right, that's what I mean.
Yeah, you can.
That you're not that the universe you're quantifying over doesn't contain.
Yes.
Yeah.
Yes.
Ranking types.
So you can never do like ID map.
Right.
Yeah.
I'm sorry. ID,
Or
the
ID.
type of map, or some, yeah. Okay, fair enough. Yes, that's exactly it. The x here, in this case, can only be replaced by int, arrow, int, or simple type, something just arrows and base types. And in this case, it can be replaced by something polymorphic. Yes?
I wanted to add, ID map actually does work in, assuming you're talking about Hindley Milner. ID map actually does work because you can make it monomorphic and then regeneralize it, basically.
Yeah, but so that's not exactly ID map, right? It's you specialize the map to some polymorphic type, then you apply it to ID, and then you regionalize it. Yes. Okay. So a second feature I want to talk about is, unsurprisingly, dependent types, because you can't really be a type theorist without mentioning dependent types.
Sorry.
And
I was going to say maybe a better, more compelling example than id map, because that generalizes out to the same thing, would be like id of run st. Run st has a for all inside of the type in a place. It's already got a rank n type, so
Yes.
you can't instantiate the polytype.
To be fair, though, I feel like my explanations for people that already sort of know about
Yes.
run st or maybe
I was aiming at
all right. So yes, it is run st.
the person behind me.
All right, so dependent types. What you basically want is to have term level information here at the type, which I'm giving the sort of the stupid example, but it does have pedagogical value in the sense that it's something we can all basically relate to, which is you have a list, but you'd kind of like to have additional information because there's an invariant in the program that you'd like to capture. Typically, some function like reverse doesn't change the length of the list. It's kind of nice to know that because then if you start with a non-empty list, then you can be sure that at some point snock is not going to raise an exception as it so joyfully does in the prelude on an empty list. So you can take this type of list of natural numbers, and you can now turn it into something more elaborate, which is basically a data type which now depends on some computational value, which is why it's called dependent types. And in this example, if you have a list with 3 elements, then it will inhabit this type, which is the vector, which is, the lists of length 3, which is vec3. All right? And of course, you want to be able to quantify, or then you don't have something that useful, which is, reverse takes some length and a list of that length, and it returns another list, which is of the same length. And so you're sort of polymorphic in the length, okay? And of course, later we'll see that, of course, you can be polymorphic in the length and in the type. And here I ask the question, which is sort of an artifact of an old version of this talk, which is this type dependency that we're adding, does it behave more like this, or does it behave more like this? Which means, does it add computational power, or does it just add expressive power? Is it just a convenience that only allows us to write the same programs, or can it allow other programs? And in particular, does this miracle still occur when we add dependent types? Does this miracle still occur when we add polymorphic types? So these are, I think, interesting questions. And it's nice for mathematicians and logicians to have a framework in which to conveniently ask these kinds of questions. And it turns out that there is a framework that allows us very easily to ask these kinds of questions. And this is called the Framework of Pure Type Systems. And in some sense, it's a family of programming languages. Okay, so it's sort of a whole. I don't know how to describe it. It's like a machine that takes as input a certain amount of data, and as output, it gives you a whole programming language that depends on that data. Now, what's nice is that it does this in a rather simple way. And in particular, all these programming languages only have one sort of type constructor. And that type constructor is what I call dependent function space. And I'm going to explain what that means. But it's basically a vast generalization of the usual arrow you see in Haskell. And also of the for all. It's sort of this overarching concept, which is why it's so useful to that list of minus x's I had at the beginning, because it's a single concept that unifies these things. All right, so here's the cliff notes on pure type systems. It's basically, it was described in the mid 80s, I think, probably near end of 80s, like 87. I should know this, but I don't. The most famous reference is Barendrecht's book. So if you Google Barendrecht pure type systems, like the first hit is going to be some giant PDF file which tells you everything you wanted to know and a lot of things you didn't want to know about pure type systems. And it's extremely expressive. So basically, this is bizarre in the sense that you have this very simple framework that's a family of programming languages, and you have one programming language that can be viewed as a logic, and that logic is extremely expressive. So there's this really weird thing going on where you have this really very large range of possibilities. It's flexible, which is basically the point of my talk. So you can model a lot of features that you find in Haskell, but also in more traditional dependently typed languages like Agda and Cook. And it's surprisingly complex. There aren't a lot of, say, open questions in type theory, but some of the open questions there are concerning these pure type systems that I'm about to describe. Okay, so this is kind of exciting for someone who's into math because, well, we like to solve open problems, and in type theory there aren't that many, so it's kind of nice to have this sort of source of open problems. It's also very frustrating because some things that seem to be obvious are very hard to prove. In particular, this one is now solved, but it was open for like 10 years, and this one is very open. And in fact, I tried to solve it several times and got it wrong, and it's a very frustrating experience. But anyway, on to the moment you've all been waiting for, which is the definition of a pure type system. So like I said, the pure type system is you give me a starting point, and I will give you a programming language. And the starting point is just these three types of data. This is just a sort, S, which you should see as a collection of elements, which are called sorts. Yes?
Are those types of kinds like in Haskell?
Yes, in some sense. We'll see examples. So you don't really need to worry about what this is. It's just a set, and then you have axioms, which are just pairs of these sorts. Okay, and then you have rules, which are triples. Okay, so you give me, a list of things, a list of pairs of things, and a list of triples of things, and in return, I give you a programming language. Now I'm going to tell you what that programming language is. But first, I'm going to give you the intuition, because otherwise, there's really no use. So the intuition is that these elements that you gave me at the beginning represent just a certain type of object, what philosophers would call a category, things that are of the same nature.
Wait,
No. Typically, a star might be the one you're most familiar with from Haskell, and it might represent the category of all types or sometimes of all propositions if you're a logician like me. Box is often used as well, and box might be the category of types, or it might be the category of kinds. Anyway, Yoda is often used just to be the category of natural numbers. So you see that these three things are sort of different nature. But right now, all we've done is say, given a name to these, and put them in a bag called S. Okay? And now, the rules, remember I had some sorts, and then I had pairs of sorts that I called axioms. Yes, and so the axioms informally say the sort S1 is of type S2, or is a member of the category S2. Okay? I tried avoiding using the word type because I use it a lot and it's overloaded. But basically, Yoda is going to be of type square, say. Okay? Because this is the category of types, and this is, the natural numbers, and so the natural numbers are a type, and so it's reasonable to expect Yoda box to be an axiom.
So if I was writing out a type system with Gensen style, those would be the rules of no.
Yes, and I'm going to do that in a moment. So.
Gotcha.
Yes.
When this translates to a type system. Sorry, never mind. Don't help me answer.
It does, and yes. So the only complicated part, basically, right now I haven't said much. I've said, okay, you have these tokens that I call types, and then you have these axioms that mean this is a member of this. So the interesting part is this, which defines the dependent function spaces. And I struggled with this slide, so don't worry too much if you don't deeply understand it right away. Basically, it governs which types of function spaces I'm allowed to build. And the intuitive idea that I tried to put into an English sentence is if you quantify over an element of S2, which is parametrized over an element of S1, then the quantification lives in S3. Okay? It's better to see some examples, but basically it's if you have something of type S1 and B of X, so you have a parameter here of type S2 whenever X is of type A, then for all X A, B of X is of type S3. Okay?
Almost all the time, S2 is equal to S3.
Yes. And
So this looks like a dependent tuple sort of smashed together with a dependent function.
so it's a dependent function.
Okay.
It's just the way I express it makes it sound a little bit like a tuple, I guess. And I'll usually write pi x ab instead of for all x ab. Okay. Just because of tradition.
Oh, okay. I got it.
When you say quantifying over, and then you give the example of universal quantification, do you mean to be abstract and imply other kinds of quantification?
No, I mean just the universal.
Okay.
And a small miracle occurs, which is when you're in a logic with sufficiently expressive universal quantifiers, you get existential sort of for free. It's kind of bizarre. In the back.
Does B have a sort on its own?
No. B sort of contains this little x as a parameter. So it doesn't really make sense to ask whether B has a sort on its own because it contains an x. Okay, and if you don't say what that x is, you can't really say what B is.
So we shouldn't think of B as like a type level function or something like that. It's like
it depends what you mean by parameter. If you think of parameterized as being a function from, then yes. But I don't think of it that way. I think of parameterized means it has a variable in there somewhere. And if you specify that that variable is an A, well then this whole thing, B of X, is going to be an S2.
It's like asking if the body of a lambda without the actual quantifier, the actual without the variables that you bind for it, has a type.
Yeah.
without any,
yeah.
without
B is-
the arguments fully being
B is a
specified.
term
Exactly.
very
So
close.
it does in so much as you specify the type of variables. Go ahead.
In Idris, would there only be one of these tuples?
Yes.
Okay.
Okay.
Universe one.
All right.
Would it be that there's one, or that there's an infinite family of them following?
In Idris, I think there's only one.
Because it has star and star, basically?
Yeah.
Oh, they don't have universe polymorph.
Yeah,
Okay.
because function types have type.
We'll get back to that particular example. Right now, I've just given you these intuitions, but I haven't said anything formal. So all I've said is you give me an S, you give me pairs, you give me triples, and I will give you back a type system, and this is the type system. And these slides are going to be terrifying to people who have never seen this symbol before, or this sort of line, this fraction here. But it's not as bad as it looks. And what it basically means is I'm going to describe the types and the programs of my language. And these are typing rules. So I'm going to tell you how to type a program. And basically, I will say to type this program, you have to do this and do this. Okay, so it's like a Prolog program in some sense, where I say, well, if I want to, compute the result of this, well, then first I have to compute this, then I have to do this, and then I have to put it together. Okay? So, you'll see later I have these lambdas. So it really is a programming language, and these things really are typing rules. And this just specifies what are the well-typed programs. Okay? This is a very convenient notation, but it's a little intimidating if you have never seen it. So I'm going to walk you through these and just give a high-level explanation. Basically, axiom here, and forget about this. Oh, yes, the turnstile. Everything to the left of the turnstile is an assumption. Okay, so for example, here I assume that X is type A, and I conclude that B is type S2, which is exactly what I wrote here. And yeah, that's type systems in a minute. So the idea is, I said if I had an axiom, then that meant S1 was sort of in the category S2, or of the species described by S2. And I just turned that into a type rule, which just says, well, if S1, S2 is an axiom, then S1 is of type S2. Okay? Unsurprising. The magic happens here, where this is a formal version of what I said on the previous slide, which is if I assume that A is of type S1, and under the assumption that X is of type A, I get that B is of type S2, then this function space that goes sort of from X is in A to B of X is of type S3. Again, this is a very general concept. It covers a lot of instances of things we know. So it's normal that it looks a little bit abstract. So those are the types, and you notice that I'm giving, this is a type, and I'm giving it a type. So types have types, and programs also have types, and now I'm giving them. So if you have a variable of, if you assume that X is of type A, then of course X is of type A, and the lambda, which is kind of the interesting one, is that if under the assumption that X is of type A, T is of type B, and B can depend on X. Okay, so B is now a sort of dependent type where it's not just a function space you're building a function space which may also say some more detailed things about the arguments. Okay, so if you have that, under the assumption X is of type A, then T is of type B, well then the lambda X of type A, T, is a program of type pi x in A, B. Okay? So this looks like A arrow B, okay, but B may depend on X. So you might have this situation right here where, you have an n and it appears. Okay, so in this case, it would be pi n vec n arrow vec n. And so surely the n appears in the type. All right. And conversely, I mean, once you have a program, you need to be able to apply it. And the only trick here is that when you apply a program to a certain argument, well, since the x here can appear in B, well, when you apply t to u, then the x gets instantiated to u. Then you say t takes an a and returns a b of x for any x. And if I apply it to u, well, then tu is a b of u. OK? So the type is now carrying some information about what application you did. And what's kind of miraculous here is that if x appears in a type, then this really feels like a universal quantification, a for all. But if it doesn't, then this, if you think of this as A or B, well, then these two rules are just lambda abstraction and application in Haskell. OK. So the last rule, and these were the toughest 2 slides, by the way, so don't worry too much if you're a little lost here, because the rest of the talk is going to be examples. The last rule is basically if t is of type A, well, then it doesn't matter if I do some computation in A, right? And that can happen because things appear in the types that are programs. So there might be some evaluation going on in the types. And what we're saying is that the typing rules don't care. You can do some evaluation in the types, and that's OK. You're not going to change the type of t. All right? In the back?
So kind of building off my previous question. So whether or not we get dependent types depends on whether our sorts are expressive enough. So
It's going to depend on this. And in particular, it's going to depend on what kinds of things you have here.
Right. So, for example, for simply typed lambda calculus, all of our sorts would just be like vanilla types, whereas for lambda for something that had natural parameters, like length parameters.
Okay. So,
are you going to talk about this?
Yeah, I am going to talk about this. I'm going to repeat the question so that it's somehow recorded, I guess. The question was, when do you get dependent types in this framework? And you correctly guessed that it's going to depend on this rule. This rule is the only thing that really depends on these triples. And depending on what kind of triples I get here, I might or might not get dependent function spaces. And I'm going to go into detail on the examples of what types of rules give you dependent function spaces and what types of rules don't. All right. Wow. So I did define beta equality, but I did it way too late. So basically, if you have lambda and you apply it to u, then it sort of reduces. You replace the x by the u, okay, which is what I explained earlier. I should have explained it much sooner in the slides. And there are like two rules that I omitted, but there's really only like 2. Otherwise, these are all the rules, okay? And if you know anything about actually sort of the theory of Haskell, Haskell has rules like these, but it has, I think, probably close to 100. I don't know. I don't know if I've ever seen them written down, but it's got like 100 of these. And here we only have 1, 2, 3, 4, 5, 6. Okay, so 6 rules for a type system is extremely few. Okay, so we have a very simple system. Yes?
Stupid question. What are the rules you omitted about?
So here, like S1 is of type S2, there's something weird appearing here, which is just my assumptions somehow have to be coherent. That's what this means. So there's nothing on the right-hand side. It's just my assumptions have to be coherent. And I haven't explained what that means. And those are the rules I omitted. It's my assumptions have to be coherent. And it's a very bizarre rule when you're not used to them, because you never see this kind of judgment in a non-dependent type system. Okay? But the fact is, when you have dependent types, you always have to verify that this is not nonsense.
Does that basically boil down to I can't prove that like 1 equals 2 or something?
Well, In proof theory, yes, everything boils down to that. But in this case, it just means that if you have non-well-typed things here, non-well-formed things here, then that throws a monkey wrench into your typing rules. It's not that important, which is why I omitted them.
Yeah, for all contexts.
Yeah. It's again, not that important, which is why I omitted them. So the rest of the talk is just understand this definition. So I can either stop here and you can ask me questions, or I can go into my nice examples, which I hope you agree with because I spent a lot of time working on them. All right. So the simply typed line of calculus of earlier is a pure type system where we give as input. Remember, you just need to list these inputs, and as an output, you get a programming language. Simply typed line of calculus is a programming language, and it emerges from this framework if you give it these sorts, axioms, and rules. So the sorts are star, which is the type of all types, and square, which is a little bit weird because you don't usually see it in Haskell, and it's just the type of star.
You can actually have them show up every once in a while if you actually.
So if you do -x polykines, do you actually see a box?
You will see. How do they phrase it? They show it all uppercase.
It's like capital box.
Ah, that's hilarious.
So you will see it every once in a blue moon.
All right. Okay. So in the simply typed line of calculus, it suffices to say that box is just there to be the type of star. Okay. And box itself doesn't have a type. It's like God. It doesn't need to have anything that contains it. Yeah, that was a poor analogy, I guess.
Type of mechanism.
Yeah, I wouldn't choose that particular term because it has other sort of definitions in type theory. All right, and the only rule is star, 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 which basically says if you have a type that is indexed, that is indexed over another element of a type, then you get a type. And it turns out that this only allows you to build simple types, okay? Because you can't actually make x appear here in this type. Why not? Because to do that, you need to have some way of applying a type to a variable x, which is not allowed by these rules, okay? And this is kind of a tough pill to swallow. So the point here is that if I don't have star box box, which I'm going to explain a little bit more later, I can't form a product which takes an x as input and returns star here, okay? And if I can't do that, I can't make sense of this guy because the type of this guy needs to be int arrow star. Okay, so if I can't make an int arrow star, I can't sort of declare vec, and so I can't make sense of this type. Okay, so if I only have star 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 here, the only types I can form are something arrow something, where these somethings are type variables. Okay, so I can do lambda x a x, and this will be of type arrow a, but I can't do the vec n of earlier, and of course I can't do the polymorphic identity of earlier, okay, because I can't quantify over types. Now I wrote a arrow a, but what I meant to write is pi x of type a and then a, so x doesn't appear anywhere, okay, and so I don't have this extra arrow construct, but morally I recover it. Okay, it emerges from this pi construction over star star star. Okay, so I just have this pi, but it just behaves like an ordinary function space. All right, so the moral of the story is that we've recovered the normal arrow from this funky pi construct and these rules. Okay, so instead of giving a next example, I'm going to give 4 next examples. I'm sorry, 8 next examples. Basically, the example we just saw and a bunch of other interesting things are contained in something called the Lambda Cube. And the Lambda Cube also only has the 2 sorts, star and square, but it has the same axiom, star of type square. And the only thing that changes are the rules. And the rules are all the form something, something else, something else. Okay? K1, K2, K2. So these last 2 are always the same. And basically, the Lambda Cube is all possible combinations of this basic schema. All right? And what's, I think, really fascinating is that every single combination gives you something interesting. Yes?
Doesn't the Lambda Cube have 8 points?
Yes, it does.
But aren't there only 4 combos?
Presence or absence of 3 different things.
Yeah,
2 to the
presence
third.
or absence. So there's like a... Okay, you'll see in a second. I actually drew the cube. All right, here's the cube. And now that I'm close to it, it looks like it's the wrong way around. But anyway, this is in front, this, and that's in back. All right? And basically, you start here in the corner, lower left, and you progressively add features until you get into the upper right-hand corner, which is the calculus of constructions. Okay? So I'm just going to name them, but right now I haven't defined them. What's quite fascinating is that I think with the exception of this one and maybe that one, all of these existed previously. They were sort of previously described type systems, programming languages. And then somehow we came up with this sort of idea of pure type systems, and it englobes all of these, which is kind of exciting. So this is simply type lambda calculus. This is LF, or lambda pi. This is system F. That one is called F omega. That one is called the second order. I'm sorry. That one's called lambda pi 2, or just lambda 2. That one's called the calculus of constructions. And these 2 don't really have important names. All right. So this is what I meant. So I gave the rules, and instead of doing a triple, I just did a pair so it would fit on the slide, okay? So this is star, star, star. This is square, square, square. This is square, star, star. So, okay, the last one here is always the last one in the triple, okay? And as you can see, all 8 systems of the cube can be represented by, so you always take this rule, and then you go through all the possibilities of adding the other rules. Okay? Either you just add this one, just this one, just this one, or add these 2, or add these 2, or add these 2, or add all 3. Okay? All right. So it's, 2 to the, what am I saying? Yeah, 2 to the 3. So one simple way to understand this is sort of just the dimension, right? It's a cube, which sort of implies that it's got 3 dimensions. So you can either go this way and basically add a pi, though I haven't added one there and there. Or you can go this way and basically add an omega. Or you can go this way and, well, add an f. Okay? So the names themselves aren't important. What's important is that each direction adds a new feature. Okay? And then, for example, this one is this feature plus this feature. And this one is this feature plus this feature. Okay? So I'm going to describe what each feature is. So first, the lower left-hand corner, you just have the simply typed lambda calculus. You have no extra features than just the lambda.
The one thing, when I mentioned earlier that S2 is usually S3, notice how the rules here only have pairs of things. It's because S2 is S3. That's the...
Yes. I know that, but I can make that...
because you had triples earlier,
yeah.
And you dropped
Yeah,
pairs.
I admit I'm not crazy about that for pedagogical reasons. So rules are triples, and here I dropped the triples because it took up too much space. and because this one was always equal to the third one. And I did the same here just to not confuse you, but maybe I've confused you more in the process.
The version I saw is Lambda Cubes. Basically, you got functions from types to types, terms to types, and types to terms, and sort of each dimension is one of those.
Yes, and that's basically exactly what I'm going to...
And you can't have a language without functions from terms to terms, so that doesn't make any sense.
Well, you could. So one thing you can make illegal is if you have first-order logic and you just have terms, you don't have lambda abstraction.
Okay.
And so that's a language in which you don't really have functions from terms to terms as an entity. Okay, you have function symbols, but you don't have the ability to create new functions. Yes.
I assume the cube commutes.
Well, you're adding a rule, so when you add the
So
rule, then you have
I don't know what it means by the cube commutes. So I mean, this is a set, so you can swap all these. All right. All right, so each of these corresponds to a dimension. I'm going to start with the last one because it's the last one I mentioned. Star, square, square. This rule adds dependent types. Okay, so this vec thing I talked about earlier, it is only typable in the case where we have this star box box product. Okay, why is that? Because vec, which you need to form to be able to talk about vec n, that is of type nat arrow star. Okay, so nat is in star is in box, and so if you want to be able to say nat arrow star, you need a product rule that goes star box box. Okay, so star box box is sort of the crucial thing you need to define vec. Yes.
Question. What do you have to do something like add primitive integers to one of these languages?
Add primitive integers. That's not really possible. Okay, it's so you can add church numerals. Okay, but otherwise there's.
You don't have to do anything to add church numerals. Just
You do actually. If you just have simple types, church numerals are basically useless. You can't write exponentiation, all right? But if you have sufficiently expressive types, then church numerals become this much more powerful thing. Other than that, the numerals you really want to add don't exist in pure type systems. That's why they're called pure, because they're not polluted by earthly considerations like integers.
I guess I should sort of assume you have a basis library and that's the end of it.
I'm sorry. So too many questions. Yeah. So you can assume you have a base library and be over with it. You can also say, well, this is just theory. We're trying to understand these basic constructs, and we'll deal with all this extra stuff later, which is what we do in practice. And yeah, that's about it. Otherwise, you need church numerals. Okay. Now, this box is one I really like because people don't often talk about it all by itself. But it's basically the system in which you have type constructors. You're not polymorphic, but you can at least write down something like list A, which is a list over some unspecified type A. Okay? And then to form this list type, you basically need to list is a function which takes as input a type and returns a type, right? It takes as input A and returns the type of lists that contain A's. Okay? So to form that constant list, you need to be able to make functions that take types as inputs and return types as outputs. And that also lives in box. So that type lives in box. So if you want type constructors, you definitely need box, box, box. Okay? So dependent types, star box, box. Type constructors, box, box, box. And for polymorphism, you need box, star, star. And this is not too hard to see because, the identity type, this for all x, it's for all x of type star, which is of type box, and some type, okay? So in some sense, this is parametrized over a type. So something in star, which is of type box. Okay, so box star star allows you to form this type. Okay, which is polymorphic. And then application is going to allow you to instantiate X with whatever you want. In particular, you can instantiate it with something that contains for all. So we have this powerful polymorphism I was talking about earlier. Yes?
What do dependent types look like without any kinds of type constructors?
This vec n?
Well, yeah, but vec is a type constructor.
So it's a type family. It's not really what I'd call a type constructor. It's a family that takes a number
Well, I mean,
and returns a type.
I mean, I'm not really sure what that would look like as lambdas, because it doesn't add any. It doesn't add any kind of types beyond.
You've got functions from terms of types, so.
So I'm saying you can assume vec exists. Okay, assume
All right.
a constructor that takes as input a natural number that returns a type.
Oh, okay.
That is
so
the kind of thing that vec
that's
is.
not a type constructor because it's not.
It doesn't take a type as input.
Okay, that makes sense. Yeah.
All right. And so all these types of things are basically things you see in Haskell, which is kind of nice. Of course, type constructors you see in Haskell. Of course, polymorphism you see in Haskell, though usually you don't instantiate X with something that contains it for all. And dependent types, not really, but data kinds is kind of something that, along with JDTs, give you something very similar to this head function. Okay? All right. So I've worked out an example. Now we are, despite my high hopes, running a little bit late. And it's kind of a tedious example, and I've sort of explained as much as I feel like I could explain. So basically I'm going to ask people here if they want me to work through this example. Okay, so it was just this complicated thing here, which expresses an induction principle, is well typed in the calculus of constructions. Okay, and this really involves the use of these product rules. Okay, so all these are product formation rules. Okay, this one is box star star. This one is box box box, and this one is star star star. Okay, so if I want to type this induction principle that quantifies over, all predicates, that's, a dependent predicate, and it has this nil a. If you want to be able to write down things like that, you need to have all these different kinds of quantifications. Okay, so it's a single quantifier, this pi, but I can use it in different ways. I can use it to make these arrows. I can use it to make these for alls, and I can use it to form these dependent types. All right. So more examples. Now I quite enjoy these examples. Basically, I've showed you all the interesting examples. I've shown you system F where you have polymorphism. I've shown you the simply type lambda calculus. Now you have this other version of the simply type lambda calculus. It's kind of weird, where you only have one base type that I call iota. And you can also form that as a pure type system, but instead of star being of type box, you forget about box and you just add a iota just as a base type, which I think is kind of neat. And the calculus of construction, I should mention that while I've heard calculus of construction so often that I sort of assume it, it's sort of the core of the Cook system for interactive proofs. So this is a well-studied system in the sense that it's used as a very concrete foundational system for theorem provers. And I don't have F omega, but system F, if I added box, box, box here, so I had type constructors and polymorphism, you notice that I have something that doesn't look so unlike, say, Haskell 98. And in fact, the core language, the core of Haskell, is some variant of system F plus these type constructors plus some other junk that I don't want to talk about. But the main idea is that they explicitly use this core as sort of a simplifying, unifying principle to build these this type system.
Is System F basically something like linear plus Rankin types?
Plus
Rankin types?
Almost, but not quite. It's more powerful. I think Ed can answer that question. I keep forgetting what sort of is missing from Rankin types to get full System F.
So something like Cliffnotes, right?
I mean, yeah, that's sort of implicit in Rankin types. All right, so the two systems I want to talk about. So star star,
We'll take that offline.
and that's the core of Idris, is just the simply typed lambda calculus, but instead of having a box here, you take star again. And that sort of makes it eat itself, and so you get this really powerful type system that, well, I mean, it's a really powerful type system that has dependent types, type constructors. It has got everything. It just has this model inconvenience that terms don't necessarily terminate. Okay, in simply like type lambda calculus, every term you could compute and eventually that'd stop. Here you don't have that property. But that's not so bad for a programming language, right? Not all programs halt. You want it to be Turing
As a
complete.
programming language, it works fine. As a logic, it has the problem that you get Hurkitt's paradox. And
Yeah, I mean, as a logic, it's inconsistent. I'll come to that in a moment.
So basically, you can actually construct an inconsistent type dependently type system with this stuff.
Yeah.
Yeah. Okay.
Well, fix is A to A implies A, so fix ID has any type. So if you're working in logic, that means you can prove any proposition.
no, it's a different paradox. Then that one's just assuming the
Oh,
hypothesis.
sorry. Okay.
So, okay, so U minus, I'm going to talk about U minus later, but U minus has this really nice feature where it adds this extra triangle. It doesn't just have star and box, it has this extra triangle. Then it has this triangle box that seems pretty innocent. And what's nice about this is that this is basically kind polymorphism. So it explains another extension of GHC, which is the ability to quantify over all possible kinds. Okay? So basically, with all these features, we've almost explained all these minus x's, which is, dependent types, polymorphism, of course, lambdas, GADTs, well, not quite, but the ability to form dependent types, rank n types, which is having for alls appear inside the arrows, and kind polymorphism now. Okay, and this one is so this is more honestly the core of Cook, because calculus of construction only has this one box, but sometimes you want to have more than one boxes. So you say, okay, well, there's box I for all natural numbers, and basically you have a box 0, and the type of star is box 0, and then the type of box 0 is box 1, etc. And then you can form all these dependent products where you have star star star, box I, star star, and then box I, box j, box k. But in this case, you really need k to be bigger than I and j.
So you can't do universe polymorphism with that?
No.
That leads to inconsistent logic.
Well,
you can.
Type is a type.
So do other things.
so if type is a type is exactly the system. Okay. So this is really the system in which the universe is part of itself. And you think
universe polymorphism is really trying to figure out what those ij's and k's are behind your back. Right?
Yes.
They're just talking about type in type, and you actually have real universes behind your back, then it's trying to find the smallest assignment of those integers that it can.
Yeah, so I have a story about that, but it's a story for another time.
Question on that: Where did Starbucks box go in CC Omega?
Oh, I guess I forgot it.
Okay.
So you don't really need it. I mean, what you can do is instead of working in star, you move everything up one floor. Okay, so the basement is flooded, so star is flooded. You move everybody up to box 0, and then you have box 0, box 1, box 1, and that's your Starbucks box. Okay, so okay, by being a little dishonest, I can say it's still there.
Wait, then why do you need star at all?
I'm sorry?
Then do you really need star at all?
Yes, you do, because this box I star star, that one, you can't like replace this with box 0. Because that leads to madness. And all right, so so the PTS is called normalizing if whenever you have a program in that pure type system, then you can evaluate it, and eventually it'll stop evaluating at some point. It will give you a result rather than looping. It's a useful property because, one, it implies decidability of type checking, which is something that we have to admit is kind of convenient. And it also ensures something that we alluded to but didn't explicitly talk about, which is the consistency if you see the system as a logic. So often, instead of seeing this as a type, you want to see it as some kind of statement that you're making, which is, in this case, not very enlightening, but in this case, it's definitely the induction principle. So it's something you sort of want to think about more in logical terms than in programmatic terms. And so it would be really nice if you could assume that logic is consistent, in particular that you don't have a proof for every possible thing. Okay, so the minus x constraints that Ed talked about last week, that's one instance of types that you would like to interpret as propositions rather than as programs. Okay, you want to be able to express that something holds rather than saying, I'm building a program and tell me what type that program has. So normalization implies these properties. So it's really nice to have normalization. What's weird is that it's very hard to predict whether a pure type system is normalizing. In particular, for both of these no's here, someone proposed the system, suggested that they were normalizing, and in some cases actually proved they were normalizing, and then later found very subtle counterexamples. And it's weird for this one because it looks very circular, right? Stars of type star, you'd think that somehow there's some kind of Russell paradox going on, type is in itself, but it's quite subtle to actually get a paradox in this logic. And so it's quite subtle, and of course, it just so happens that getting a paradox in this logic means building some term that doesn't normalize. And it's really hard. The term is gigantic, and it's very hard to read. And U minus is even more perplexing because there's no circularity, right? Stars of type box, boxes of type triangle, but triangle isn't of type box or star, so you don't get a circularity here. You do get a circularity here where, boxes of type star and then boxes of type triangle and then triangles of type box. So, here you go up and here you go back down. So you sort of have a circularity, but you already have that circularity here, right? Stars of type box, box, star, star.
U minus is killed by Girard's paradox, right?
Yes. No.
No.
It's Gauguin's paradox.
Huh?
But
okay.
So U is killed by Girard's paradox.
Okay.
And if we want to be historical sticklers, which of course we do,
yes.
A U minus was proved inconsistent by Gauguin a few years later.
Okay, thank you.
Subtle paradox again. So system F has a sort of miracle where the circularity is not broken, and CC looks a lot more complicated than U minus, but it still is normalizing. Quite hard, in fact, to prove, by the way. But U minus is not normalizing, so it seems completely random, this pattern. It seems very hard, given as input sorts, axioms, and rules, you tell me if it's going to normalize or not, all right? And this is, a completely open question. Nobody knows even if it's decidable, so we don't know anything about this question. In general, it's an excruciatingly hard question. All right. So I had more slides about this in my other talk, but they were getting technical, so I excised them. So PTS, so I showed that you could capture this powerful type of polymorphism, the for all x, x arrow x, and you instantiate x with whatever you want. But you can also do the other version where you can only instantiate x with monomorphic types. How do you do that? And this is a very clever trick. And this is where I'm kind of happy that I kept the triples, because you don't have this pattern, K1, K2, K2. What you do is you add this extra star hat, and star hat is intuitively the type of polymorphic types. Okay? And now instead of having box star star, which is what you have in system F, you have box star star hat, and then box star hat star hat. So you can start quantifying over types and get into star hat, but you jump out of star, okay? And you can't form function types at this level anymore, okay? You have the simply typed Lambda calculus, so star star star, and then you have these other guys. And it turns out that if you do this, then you have exactly the behavior you wanted, which is you can only instantiate the for-alls with monomorphic types. Yes? I'm sorry. I hesitate to say yes because Hindley-Milner is, it's unclear what that means. Is it an algorithm?
What's written on the Wikipedia page?
So Hindley-Milner type system, I'd say yes, but it doesn't have let polymorphism, which I'm not sure is officially part of Hindley-Milner or not. So the two caveats are, one, Hindley-Milner in my mind is an algorithm and not a type system, and two, there's this let polymorphism that you don't really have here. Okay, but essentially yes, you have something that's very close in spirit to what Haskell 98 allows. And here's another neat trick. Without data kinds, in some sense, you have these sort of funky dependent types that sort of depend on things that are not programs. So you have type-level terms, and then you have programs that have values, but never the twain shall meet. And you can model this in pure type systems, which I also think is amazing, which I call type-level data and program-level data. So you have just two copies of everything, the type level and the program level. And I call them star T and box T and star P and box P. And then you have sort of two copies that live next to each other. And then you allow types to depend on these type level data pieces by allowing this star box box. And if you erase all the P's and T's, what you get is this guy right here with ordinary dependent types. Okay, but if you don't erase them, if you remember to separate out your P's and your T's, you get dependent data, but it's not programs. And you get programs that have dependent types, but programs can't themselves appear in the types. So this is kind of cool. And this is quite similar to what GADTs capture.
So is that sort of like separating propositions from terms, so you don't get
yes.
stuff like I add fix and suddenly I've got an inconsistent logic because it's not
yes.
a proposition? Okay, good.
Though there are subtleties. It's very easy to get an inconsistency. Okay, I guess I've gone over, which I feel terrible about because I thought I was well under. So U minus has kind polymorphism, and U minus is inconsistent, as I said earlier, because you have non-termination, which I said is maybe bad news for polymorphic kinds. I wrote constraint kinds, but I meant polymorphic kinds. Basically, if kind polymorphism is impredicative, as it is in U minus, it's not? Yeah. Okay, well then scratch this remark. If it was, then you'd have an inconsistency at the type level, and you could prove things in these constraint kinds that didn't hold. In particular, you could prove some very strange equalities that didn't hold, like nat, twiddle bool, and that would be pretty bad news, I think, for Haskell.
I don't think we care. You can already do that with fixed points.
You can prove nat twiddle bool?
Sure.
And doesn't that break subject reduction, type preservation.
No, you have to evaluate.
You have to evaluate the coercion. The
Yeah,
proof.
you just can't.
Wasn't
erase-
yeah?
erase
So
your
that's
proofs.
true if you're in a strict language, but doesn't the fact you're in a lazy language?
The witness of that is evaluated strictly, so that portion of the language.
Oh
is
wow, jeez, man.
We're strict enough that we're strict enough that we're not going to
That's
start
terrible.
scribbling at random memory.
All right, so okay, Haskell is even crazier than I thought. Conclusion: pure type systems are just sort of a model functional language where you have this very simple syntax, only a few rules, less than a dozen, which for a real language is crazy. But they explain many aspects of the Haskell type system, right? They're this very unifying framework that allows you to take all these crazy minus x's and try to make sense of it in a single framework. And they're fine-grained, so you can use these tricks to sort of limit the amount of power you have, and so sort of help the programmer, control this crazy power of dependent types. So you can sort of force monomorphic types. Typically, if you want to infer types, then that might be a good idea. You can separate, type level data and term level data. So this is a really neat feature that's enabled by this very simple framework. And of course, one thing that's nice is that, for example, you can prove subject reduction once and for all pure type systems. Type preservation. And you can prove a bunch of other generic things that you're not going to have to prove again. And that, for a mathematician, is quite nice. But there are still some very hard questions about pure type systems. Because they're so flexible, because they have all this power, it turns out to be a very interesting object to study, and there are some pretty elementary questions that haven't been answered. Wow, and that was my last slide. So thank you. And I think